Welcome back, welcome back, welcome back. I'm Miss Lisa. This is my YouTube channel where we talk about math and science. Like, share, subscribe. I have a goal, 1,000 subscribers. So don't just like it, don't just share it, subscribe so I can do YouTube Live. That's why my goal is. So this is physics. This is a class primarily designed for homeschoolers, but if you like the way I explain things, come on in. For homeschoolers, we are going through this book. It's an old public school book where it's cheap. It's a cheap book. That's why we do it. And it actually teaches the same physics in the same exact way as the public school I'm working at now. So don't worry about it being a little bit older. Nothing's changed. Physics is the same. We keep quoting Newton, who was figuring out things hundreds and hundreds of years ago, and it's what you're going to be learning now. So there are things changing in physics, but just not what you learn in high school physics right now. So you're safe with your old book. And it's cheap. And you can get the teacher's edition for cheap, and you can get the test, and you can get the lab book for cheap. So things that if they were new would cost hundreds of dollars, you might spend tens of dollars on instead. All right. So what we're going to talk about this time is, that was our last one, momentum. We're off of momentum. That was the last chapter. We're going to talk about machines, simple machines. So work, energy, and simple machines. And I've also got, if you listen to this one and you think, I need to know more about this, I also have a physical science video on the same thing that explains it even more. So if you need a little more explanation, go find the physical science video. It's already posted, I'm pretty sure. I'm doing these in advance. Right now it's fall break for me in public school, and I'm making a lot of these videos so that I don't have to later, because it ends up, because I don't have enough subscribers, it ends up taking like my whole Saturday. So I work all week at school, and then all Saturday is taken up making these videos, which I want to do. I want to bless the homeschool community with these, but I want to do it faster. So like, share, subscribe, so that I don't get grumpy about it and I keep loving it. Right now I'm loving it. I think it's fun. So anyway, work, energy, and simple machines. First of all, let's talk about what is work. And you're like, I know what work is. Of course I do. I have to work all the time. I have to do homework. I have to do yard work. I have to do chores. I know what work is. Well, there are certain terms that they have one meaning in everyday language and another meaning in science. Remember, I told you the word theory is one of those, that in everyday language, theory is just an idea. I have a theory about that, and it can be my crazy theory about anything from politics to baking. It can be anything, but it really has no basis in scientific fact. But a theory in science had repeatable, observable experiments done to it hundreds and hundreds and hundreds of times, and it's a model where we are getting better and better at understanding it. And what makes that confusing, I've told you before, is that even in science, we'll switch. We'll use it our regular everyday way, and then we'll pivot and go use it the science way. So work is one of those terms that has an everyday definition and a science definition, and the science definition is much more narrow. And this is the science definition. Work is when a force is applied and it moves something a distance. So I could push on this wall all day. I could work up a sweat. I could burn a lot of calories, but I would have not done any work unless I could move the wall. Same thing, like you might think very hard and like you did your homework and you thought very, very hard, but if you didn't move something, by the physics definition, you did no work. For it to be physics, you have to apply a force and move something a distance. And that's what work is and nothing else. So it's a narrow definition. Now, like the other chapters, we're going to talk through the ideas in part 1, and I'll go back and show you the math in part 2. So there's a formula with work, and in our first problem, it is pretty easy. Like I said, there are parts of physics that's taught in physical science simpler. This part of physics is pretty much taught just like it is in physical science and physics. So it's one of the easier chapters. So if you didn't like the last couple, because they were pretty hard because we had to use trig and stuff, this one's a little bit easier. I think we do use some trig in this one too. You're going to get good at trig. You get to do the fancy math, and the fancy math is fun. All right, so work is force times distance. We do a work problem. Okay, now remember I also told you that when I was your age, I was under the misunderstanding that there was just this huge number of millions of word problems from my teacher to make up, to torment me with. But now that I've done this for decades, and we will not talk about how many, I have realized there are only certain problems that we just do over and over again. Classic problems. You know, we really want to know how tall this certain tree is. We want to join a video rental club, and then we will like change the situations, but the problem stays the same. You change the number, you change the situation, but the problem is exactly the same. Well, with this stuff we're doing here, one of the things we're going to be very concerned about is having a handle. So we can push a lawnmower, we can pull a wagon, but that gives us our angles where then we can use our trick. So we're going to do some work. Do some work problems where we're finding out the forces, and we get to make it a triangle, because once you have that handle going out, then you can draw your triangle and you can know your angle, your theta, and then you can do the math. So that's just a huge concept for students, the fact that there's only a certain number of problems. So you learn the problems in your chapter, and you know that the problems on the test are going to be like the ones in the chapter, just different numbers. And you can even memorize them. That, you know, when I see these knowns and unknowns, I know step 1, write my knowns and unknowns. Step 2, this is the formula I'm going to use. Step 3, I substitute. Step 4, I use trig or whatever. And when I started getting really good at science, I was pretty good in high school. Like, I made A's and I was in all the AP classes and stuff like that. But I still felt shaky. I still felt like not super confident. I always felt like the boogeyman was around the corner, the big bad problem that was going to knock me on my hiney. But once I started realizing, nope, there's only certain problems that are going to be on this test, and I started training for them, not just understanding it when the teacher did it, but getting where I would practice it myself, and not just do the problem one time. I would do the problems over and over again. That as soon as I saw that problem, boom, I was off, and I could do it real fast. Because especially in college, you guys are mostly homeschoolers. You have all the time in the world. You can dawdle. How many times did I say to my own homeschool kids, quit dawdling and do your work? Focus, go do your work. You know, we could do something fun if you would do your math a little faster. Probably your mom has said these same words. So once I realized, just for me, that to do them fast was a benefit, because I'd get to the point where I could just do it so fast. Because when you get to college, you have a limited amount of time on the test. And it doesn't just test if you know how to figure out the problems. They test if you can do them fast, because you run out of time, and the ones you didn't get to, you get zeros on. So you need to start learning to do it quicker and do it, but not just fast. You have to be good, because with me, I'm slightly dyslexic, and I have to be careful not to go fast and just flip all the numbers upside down and get them wrong and change the problem, because I'm flipping things all over the place with my dyslexia. I used to say I was dysgraphic, not dyslexic, because I usually can read okay. It's when I write that I flip things. But then, now that I've gone back into education, they have tools that for kids that they didn't have when I taught last time. And they have it where they can change what they're reading on a computer to a dyslexic font, one that's better for dyslexia, reading dyslexia, not writing, not dysgraphia. And so you can take whatever you're reading and you go over on the computer and you click the font. And when it makes the dyslexic font, I'm like, it's like I can breathe deeply and I can read so fast. And I realized, rats, I am partly reading dyslexic too, because I have to read slower. I have to concentrate harder. It's like I tighten up on the inside. And when I have that dyslexic font, it's just like, this is luxurious. This is so nice. So any of you moms out there who are dealing with the dyslexic kids know that there's some tools out there now that are pretty cool that you can get that can help the dyslexic kids read better. It's a way of making the letters. See, for a long time when I was a kid, P, B, D, and Q were all the same letter. And I remember third grade looking around and I'd been reading since I was 3. My sister taught me when I was still 3 with flashcards, see and say, and I memorized the words. And I would memorize the whole words, and the whole word was a different shape, so I could learn it. But then when I got in third grade, I remember looking around the other kids going, how do they know the difference between P, D, B, and Q, and I don't? And looking around thinking, they have some secret hidden wisdom that I don't have. And it was that I was dyslexic and they weren't. Oh well, it's a little humbling, but that's all right. We all need something to keep us humble. All right, so we're going to do problems with handles and come back for part 2 and you'll see the problems. So they call it force and displacement at an angle. Problems with handles, classic problems. The next concept is power. A long time ago, my kids were in some play or something where they had about power, and there was a chair. P-O-W-E-R, power. P-O-W-E-R, power. It doesn't really fit. But every time I see power, I have to say the cheer. Okay, so what is power? Power is a rate of work. It is work divided by time. So how fast the work is done is power. It is measured in watts, and it's how we pay, and that's what makes it confusing. It's how we pay our power bill. It's how we buy electricity is in watts and kilowatts and kilowatt hours. So, but power is how fast work is done, and we will do a problem with it. Power is work divided by time. So how fast work is done. We did last year the lab that is on page 204. You walk upstairs. You calculate the work done, and then you see how long it takes you to do it. So we had Zach, I think was our student last year, who went up the stairs. But was Josh? Yeah, I guess Josh was in that class. I was trying to think, was Josh and Zach in the same class? They were. So we had Zach walk up the stairs, and we measured how high the stairs were, and we calculated his power. So you can do this lab. This is one that takes absolutely no fancy equipment, and you get to do a little good physics math with it. So go find some stairs, walk up them, do the measurements. You might need a meter stick. Sometimes meter sticks are hard to find, but you can also find a measuring tape. Just find one that's got centimeters and meters, not just inches. And sometimes it's a little hard. I get irritated that Home Depot sells yardsticks, and how hard would it be for them to put those centimeters on the back of it and make it a meter stick? Home Depot, are you listening? I'm talking to you. I want meter sticks at Home Depot, not just yardsticks. All right, machines. What is a machine? You're like, I know what a machine is. Why am I wasting my time? A machine is something that makes work easier. And you're like, yeah, I knew that. But so machines give you a mechanical advantage, and there's a math problem to do with it. Ha, I see, there's something you didn't know. And so the mechanical advantage is the resistant force divided by the effort force. So your energy in divided by goes into what comes out. And how machines work is they make it where there's less effort force, but usually it's a trade-off somewhere. So like it might be a machine that makes it where it takes less force to do some work, but you have to do it a longer distance, usually is what that is. So when we talked about torque, I already taught you about torque, that torque is a rotational force that we push on and remember I told you that torque equals force times length of the lever arm. You can have less force if you have a longer lever arm, but you're going to move it a greater distance. So there's always a trade-off for that mechanical advantage. So there are different types of simple machines. One is a wedge, so that would be this shape, a ramp. You can use this ramp to move something up. Imagine if it was me and I had to hop up this ledge to get up here. But I could walk this longer distance and it would be easier, wouldn't it? I doubt I could hop up that if it was too high. I'm not a good jumper. But I could walk this long way. So I'm trading off a greater distance for a less effort force. Another one with this ramp is I can take this ramp. Imagine that this is a piece of paper. I had it here somewhere. Let's see if I still have it on my desk here. Nope, I lost it. Look on the floor. Is it on the floor? Nope, it's not on the floor either. Anyway, just imagine this. If I took this and I wrapped it around a stick, then that would be like a ramp that you walk up all the way around. Do you imagine that? Like the Leaning Tower of Pisa. You could walk up it going around and around and around and around to the top. And that's really still, so a spiral staircase is still a ramp. It's just a ramp that's been coiled up. Now imagine that I take my coiled up ramp and I put it around a piece of steel, a straight, like a nail. And I put a little groove all the way around it. Now I have a screw. And this screw makes it easier to get the piece of metal in the wood, but I have to go a much greater distance. Turn the screwdriver instead of bam, hitting the nail. So a screw is actually using this simple machine of a ramp. If I take two of them and stick them together, I have a wedge. I can take that wedge and use it to change the direction of the force. I can hit down on it with my hammer and it's going to push out and I'm going to be able to split a log. I couldn't split a log very easily with my bare hands. I am not the Hulk, even though I'm wearing green today. But I could use a sledgehammer and use that inertia that we've learned about of the hammerhead going down, hitting the wedge, and I can use the natural physiology of the wood, the xylem and phloem going vertically through it that you learned about in biology class, and we can split the wood using that simple machine, which is a sort of like two ramps put together, and it's a wedge. So you can use it for a doorstop. It changes force. Okay, another one that we can do is a wheel and axle. So anytime you have a wheel with something in the middle, then you're using torque, and that makes it easier because you can have a bigger lever arm and less force. One type of that is using a pulley. Now, pulleys, depending on what it is, they give you different mechanical advantages. Okay, so here I've got a pulley. I've got a rope going up, a rope going down. Here's my heavy thing I'm trying to pick up. Now, the advantage to just one pulley, I can pull down on this rope and I can pick my load up. Why is changing the direction of the force going to help me? Why is this machine useful? And it's because, let's see, you can't see my tummy. My tummy just honestly has a little fat on it. And I can use that fat, and I can use all of my fatness, my bones, my skin, my internal organs that usually do no work in picking stuff up, and I can use my weight to hang on the rope, and that will assist me picking it up. Instead of just having to use my muscles to pick it up, now I can use that little Debbie I ate and I shouldn't have, and I can use it to help pick the thing up. So redirecting forces is one of the things machines do. Sometimes it doesn't change the weight of this thing I'm picking up, but it's easier to pick up because I redirected the force. Now you can add more pulleys to a pulley and get a system of pulleys, and so I can put another one on here, and I can make the rope go around it back to there, kind of thing, like that. And I can have a system of pulleys, and what it does is it makes it where there's much less force needed. It uses more than your fatness. What the extra pulleys do is they make it where there's less force, but you pull at a greater distance. You can add lots more pulleys, and like a whole bunch of them, and even someone as scrawny as me and weak can pick up an engine out of a car, and I've done it before. When you have a bunch of pulleys, it's a machine called block and tackle, and usually it's a chain, not a rope, and you pull, 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 pull the chain, and the engine barely moves up or down. But I've done it, and it's like, it's easy. It takes a while, but a person can use a block and tackle and pick up an engine. I feel like a superhero like that. So all extra pulleys give greater distance, but less effort force. Okay. Now, you can also calculate the efficiency of a machine, and that's equal to the work out over the work in times 100. Let me show you how I remember this formula. It is the efficiency equals the work out over the work in times 100. Now, I get rid of the W's, and I say out over in, and it looks like a Disney dotted I. So I can remember that out goes on top and in goes on bottom. Out divided by in times 100. And that's how you do efficiency. Now, all machines lose efficient. The more complicated the machine, the less efficient it is. And no machine is 100% efficient. But a good example is your car. Your car is a very complicated machine. And if the gas you put in it, only about 20% makes it go forward. What you buy the gas for is to make your car go forward. But 80% of it is lost to heat to the environment. You put your hand on the hood after your car's been going and it's warm. All those parts with friction, and also you have combustion going on in your car. We have combustion engines where gases put into the piston, into the little chamber with the piston underneath it. It's sprayed in a mist. The spark plug lights it, and then it explodes. And that explosion has heat to it of the gasoline burning, the gasoline vapor, and then it shoves the piston down, and all the pistons being shoved down at different times is what turns the big rod, then that energy is transferred to the tires, and then it makes it go. And I don't know if your book teaches this, the physical science book does. I don't know if your car shows how a car works. No, it doesn't. But it's out there. It's on the Google somewhere, so you could go look it up. All right, another kind of simple machine are levers. Now, I say lever because I'm from the South, but other parts of the world say lever. And I had never heard lever until back in probably the 80s, a kind of soap came out that they were selling lever 2000, lever 3000, something like that. And I'm like, lever? What's a lever? And then you saw the box of the soap and you said, oh, a lever. But we say lever. But one time I was saying, and this happened a long time ago. One time someone asked me what I was teaching, and I was teaching physics and physical science. And I said, oh, we've been learning about levers. Well, the person I was talking to thought I said lover. No, that would be biology class. This was physics class. But ever since then, I'm like, this was someone who they were Southern, but they said lever instead of lever. But ever since then, I've polled my classes I teach, and I'm like, do y'all say lever or lever? And they always say lever, and it's because I'm in Georgia, and we say lever instead of lever. So whenever I say lever, if you're from somewhere else, just substitute lever, and you'll know what I'm talking about. So a lever, a stick that you move for a machine. So this is a very fancy machine. It is a stick. All right. So there are 3 classes of levers. And the first one is a teeter-totter. The part that stays still is called the fulcrum, and the fulcrum is in the middle. So if I push down here, it goes up over there. Now, why does this machine give you advantage? Well, for one, you've got torque. So if this is long enough, then you're going to have much less effort. And then the other thing is, once again, I can push down to pick up. I can use my fat. I can use my fatness. Down is easier than up, because up you got to use your muscles. So this is a first class lever. So whenever you push down and it goes up, like a teeter-totter, my physical science book has this little thing, and the first class lever is a shovel. You push down, the plant comes up. The fulcrum, the part that stays still, is sort of in the middle there. You push down, the end of the shovel comes up. So that's a first class lever. The second one is a second class lever, and that's like a wheelbarrow. You pick up here, and the fulcrum stays still on the other end, and it picks up there. Your load is here that you pick up. It is using torque also. The length of the lever arm makes it easier. If you have a wheelbarrow with very long handles, it's easier than one with short handles because you're using torque to manipulate the force where you have to use a longer distance. So this does give a mechanical advantage also. Here's our wheelbarrow. The fulcrum is the tire that's still a wheelbarrow also uses the circle, the wheel and axle, like the pulley does. So that reduces friction by using a wheel, and also the size of the tire. If it's a bigger tire, then it's less effort too because of the whole advantage of the tire. So here you're using the wheelbarrow. Your fulcrum, the part that doesn't move, is the opposite end than you, and it does give you a mechanical advantage. I can carry a bunch of firewood in my father-in-law's wheelbarrow. We don't have one, but they live next door and we just borrow theirs. So we'll get firewood, and I can carry a bunch in the wheelbarrow, way more than I can carry with these mighty arms. Okay, so the third class of lever is like a rake. It's where the part that stays still, a broom, a rake, anything like that, the part that stays still is up where the effort is. They're together. So you hold think about how you rake. You hold this part still, and then you move things. So the fulcrum is up here. What you're moving is at the other end, at the opposite end. You're at the end where the fulcrum is, and what you're moving is at the other end of the stick. This actually gives you no mechanical advantage. What it does is it extends your reach. It's easier to rake leaves than it is to get down on your hands and knees and pick them up. So if the effort's the same, it's nice to have a longer reach. So that's our brooms, our rakes, anything like that where you hold part of it and move the other part. So that's our third class of lever. Now, the next idea is a compound machine. A compound machine is where you take simple machines and you put them together to be a more complex machine. The bicycle is the thing that your book uses. It uses wheel and axle. It uses torque on the pedals as you push them. It's got all kinds of machines added together. Let's see. All right. And they talk about how it does that. All right. Okay, and then we have a problem figuring out with the bicycle. And then the last thing it talks about is you. There used to be an old Schoolhouse Rock. I'm a machine, you're a machine, something, 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 something machine. You should look it up. They sing better than I do. Anyway, you're a machine. Your body is an amazing machine. And one of the most amazing parts is walking. Walking is very complex. And if something happens to it, it's hard to get back. My mom had a stroke a couple of years ago. And boy, something that had been so easy the week before, the week after that, she's in rehab trying to learn how to walk again. And it was a big old pain. She got better. But then I think she had another stroke and it got worse again. But anyway, if you ever know anybody who's had to learn how to walk again, it is not easy. So walking is amazing, and your whole body is just amazing. But with walking, every part of walking is physics all working together. Your toes actually help change gears. They help you in your walking effort. Your foot, all those little bones in your foot and muscles. And if something goes wrong, boy, is it a pain. I run. I'm a runner. That's one of my sports. I run and I lift weights. I know you are going, she does not look athletic. I am kind of for a middle-aged woman. But I hurt my foot with plantar fasciitis, I think is how you say it. The bottom of my foot was really hurting, and I had to do all these exercises, and it was just these few little muscles on the bottom of my foot, and boy did it cause a problem with my running. Turns out that my shoes had worn out. I had good running shoes, they were Nikes, but they still looked good, but they just weren't fitting right anymore, and it made my toenail come off. How gross is that? And the bottom of my foot hurt, and so I had to go buy more expensive than Nike shoes. Nikes are bad enough. But I got some that they're Ms. Uno, and it's like running on clouds. It's awesome. And now they're starting to get worn out, so I'm gonna have to buy some more. But running's a good sport because you can do it. It takes very little equipment, just some shoes but buy good enough ones that you don't make your toenail come off or you get your foot hurt. And then you can just do it your whole life. It doesn't, take a whole lot of equipment. You can go do it out in nature and see how beautiful everything is. So I really enjoy running. So, and when I do, my feet are amazing machines. All right, so that's chapter 10. Come back for the math. I'm Miss Lisa. Like, share, subscribe. Science is great. Physics is great. Math is great. I'll see you soon.